In the next problem, we are analyzing a beam with homogeneous load distribution. As you can see in the illustration, 2 points at both ends of a thin and long beam are fixed. The points fixing the beam here are called simple support. This is similar to the support in the truss problem, in which the 2 ends are pinned together. At the simple support, the rotation is free, but supported from the bottom. Let me explain about the deformation of a beam in more detail. As this beam bends, the distance between the both ends decreases a little. The amount of the decrease is so small, and it is not shown in the diagram. But you should be noted that the beam is not constrained along the longitudinal direction. As shown in the diagram, the beam is loaded only upward and downward. Then the beam is supported at 2 points. In this problem, a beam of length L is subjected to a uniform distribution of a load. Now, we are arguing about the uniformly distributed load. The load, the unit of magnitude of the load in the previous problem, is Newton. In this problem, the load Q is distributed uniformly. The unit is Newton per unit length. For example, in this illustration, the length of the beam is L. So, the product of the length L and the load Q is the total force acting on this beam. Since both ends of the beam are simply supported, you can imagine that the beam bends downward to become convex. However, we are not arguing about the deformation of the beam here. The beam is simply supported at both ends, and then the upper surface of the beam is subjected to uniformly distributed load. We are now determining the shear force and bending moment generated at each section along the beam in this condition. We focus on the reaction forces that is supporting both ends of the beam. The reaction forces at both ends are reacting to a load QL acting downward. The total of distributed load is QL, which is the product of the distributed load Q and the length L. Since the total load is supported at both ends, the reaction forces at each point is QL divided by 2. You should here understand how to calculate the reaction forces QL divided by 2. We are now cutting this beam at X on the X-axis, and then consider the balance of forces at the cross-section. We have cut the beam at position X. Total load of Qx, distributed load, is acting downward. So we can assume that the total load Qx is applied to the center of gravity. The point here is that the total distributed load is approximated as a load at the center of gravity. Now, we are considering loads on this section of the beam. One is the reaction force QL over 2, and another is the distributed load acting downward Qx. Is there any other force? Note that this is a cross-section at a point on x-axis. So, a shear force is needed on this cross-section. You should recognize the shear force Qx as that acts on this cross-section. Let's consider the balance of the forces here. We have a load downward Qx and another reaction upward R. Considering that they are balanced, we get the equation. Substituting Qx and reactions of F, which is Qx, Ql divided by 2, is this equation. From this equation, you can get Qx and the shear forces as introduced above. You should understand the derivation process of the shear force introduced so far. The shear force is given as a linear function of x. This function is symmetrical at the center of the beam. The point at which x is L over 2. You may notice that at the center of the bridge, the shear force is 0. So, the shear force is not acting here. There are two forces balanced by the shear force Qx. One is the reaction force upward, F, and Qx acting downward. Considering the equation that describes the balance of the forces, we can derive the shear force, Qx. Next, we are thinking about the bending moment with respect to the illustration. As before, we are cutting the beam at x on the x-axis and then considering the components of the force and the moment. From the left, R acts on the beam. We are considering the moment caused by this R at this cutting position. The moment Rx is the product of the force R and the length of the arm. The force F, which is Qx, is acting on the beam downward at the center of gravity. Then, the moment caused by the force Qx acting at x is Fx divided by 2. This is the moment acting downward. We have just shown two moments acting from the left side on the positions along x-axis. The beam is cut off at x on the x-axis. Now, let's consider the moment acting from the right. This is the bending moment acting on the cross-section. Without the moment acting on the cross-section balanced with the moment on the left, the beam rotates. So, note that mx should be acting now. Thus, we have mx and rx and fx over 2, and these three are in balance. Taking these things into consideration, we get the equation to describe the balance of moments. Considering fx over 2 is negative, the moments at the left cross-section is Rx minus Fx over 2. This is balanced by the moment at the cross-section of right, Mx. What we have got here is the distribution of moments, the equation for Mx. As represented in this equation, Mx is a quadratic function of x. This is a quadratic function such that it is maximized when x is L over 2. The distribution of the shear force and this distribution of the bending moment that we have just obtained is shown here. These diagrams are the SFD and BMD for this problem. You can see that SFD is a linear function and BMD is a quadratic function. We are not going into detail here, but the SFD is derived by differentiating the BMD by x. If the BMD is quadratic, the SFD is the derivative of the quadratic function, a linear function. You may notice that the SFD is the derivative of the DMD. You can check if SFD and BMD are consistent with each other by differentiating the BMD.